Okay, welcome to lesson 16, mechanical waves. We are done with angular momentum and conservation of angular momentum. At least we're done until WPR number 2 and then the T, of course. But lesson 16, we'll start to build the blocks for the rest of the lessons in the block before the test. So we'll get into superposition, we'll get into sound waves, and then next block, around spring break time, we'll get into optics, so we'll talk about electromagnetic waves. But today we're talking about mechanical waves. And so let's briefly describe what mechanical waves are, and we'll talk in general terms about waves, and then we'll derive what we call the wave equation, and then we will talk about the speed of a wave on a string with tension. Okay. So mechanical waves require three things. Those three things are a source of disturbance, some medium containing elements that can be disturbed. So the key here is that mechanical waves require a medium to be transferred. And then there has to be some physical mechanism by which the elements of the medium can influence each other. And the two types of waves you need to know about are longitudinal and transverse. So longitudinal waves, that means that the elements in the disturbed medium move parallel to the direction of wave propagation. So if you think about the elements in a slinky oscillating back and forth, the wave or the energy is actually being transferred parallel to that direction. And then we have transverse waves where the elements in the medium move perpendicular to the direction of wave propagation. So think about the waves in the ocean, right? The water is going up and down, but the wave is moving towards the shore. And you've probably been in a situation where you're out there waiting for a wave on your surfboard or on your boogie board or something, and so when a wave passes you by, you move up and down, but the wave moves towards the shore, so that's a transverse wave. And so we've kind of described what waves require and types of waves, but if you had to define a wave, that's a different story. And so this is one of those things where you kind of know it when you see it, something that's hard to describe, but I would describe it as a periodic disturbance traveling through a medium, at least for a mechanical wave. So we'll see that periodicity when we derive the wave equation. So let's go ahead and do that. Okay, so now we're going to derive what we call the wave equation. And in order to do that, let's draw a wave, and we'll talk about it, and then we will derive the equation that describes that wave, and then you'll see some things come out. Okay, so here's a coordinate axis for us, and we're going to draw a wave, and this wave y is a function of x. And so if we draw the wave at some time t equals 0, we might get something that looks like this. And if we were to draw the wave at some later time, we might get something that looks like this. And so we can see that the speed of the wave or the direction of travel is indicated by this speed or velocity v to the right or in the positive x direction. And the distance the wave travels in that time is the speed of the wave times time, so vt. So this wave is a sinusoidal wave, and that means that it has the same function as a sine wave. And it also can be referred to as a traveling wave because the wave does not interact with anything else as it travels along. Okay, so let's take that and we can move that off to the side here. And let's look at some other characteristics of the wave. Okay, so again we have a coordinate axis, and our wave is, now we're going to say it's a function of x. And so this is a snapshot of the wave moving through a medium. So we're taking it at one time. So we can see the wave as a function of distance. And so the wave will look something like this. Something like that. And there are some parameters we want to define, such as the amplitude of the wave. So this is the maximum displacement from 0. And then we also have the wavelength of the wave. And that's the distance between two crests or distance between two troughs in the wave. And you've seen this before. Okay, so that's the wave as a function of x. And now we can take that wave and move it over here. Okay, and now let's look at wave as a function of time. And so with this coordinate axis, we will look at y versus t. And this is basically us tracking the position of one element of the medium as a function of time. So as time ticks by, we're watching what happens to one piece of the water in the ocean, let's say. And so that wave will look, as we've seen before, like this. Something like that. Okay, so we still have the same parameters. So this is still the amplitude of the wave. And now this is not the wavelength anymore, but if we're plotting the wave as a function of time, this is the period. So this is the time it takes between successive crests or successive troughs to pass through one point. Okay, so now we've talked about that. We can move that over here as well. All right, so now we're set to actually derive the equation that describes a wave, and so we've already said it's a sinusoidal wave, and you would expect that the equation would have a sine or a cosine term in it, and you'd be right. So let's get started with that. To start, let's look at the second graph we drew, which is y versus x, or y is a function of position, or x. And so we see that at this instant, if this is time t equals 0, then the wave function should have the form y of x equals ym, or the amplitude, times the sine of ax. And in this equation, ym is again the amplitude, x is the position, and then we want to determine what this constant a is. So if we were to look at y of 0, that equals 0, right? If we're looking at, this point on the graph. And so the next point at which y equals 0 is going to be 1/2 of a wavelength away. So y was 0 here, y is 0 here, but that's a full wavelength. But the next point between this equaling 0, the next point is right here. So this is 1/2 of a wavelength. And we can write that like this: y of lambda over 2 equals 0. So if that's true, 0 equals ym sine a times lambda over 2. And for this equation to be true, then we know that a times lambda over 2 has to equal pi, because that will give us a value of 0. And so if we solve for a now equals 2 pi over lambda. And so we can rewrite that equation for the position of the element of the medium as y of x equals the amplitude times the sine of 2 pi over lambda times x, or we can also write amplitude times sine of kx, where k equals 2 pi over lambda, and that's what we call the angular wave number. And that has units of radians per meter. Okay, so we've only been looking at this graph here, and if we wanted to get a more general equation for the wave, we know that the wave is not just a function of x, but it's also a function of t, or time. So let's expand this to take stock of what's happening as a function of time as well. Okay, so let's take all this and we can move that over here. Okay, so our wave equation, if we write it in terms of y and x, x and t, that is ym times the sine times the sine of kx minus vt, right? So if we know that the wave is traveling with speed v, at some later time, it will have this position, so minus vt. And so this negative sign arises from the fact that the wave is traveling, right now we're assuming it's traveling in the positive x direction. If it were traveling in the negative x, this would be a plus sign. And so we'll see that when we write the general form of the equation, but for now we'll assume it's traveling in the positive x direction. So we have ym sine of kx minus vt. Okay, so we know the wave is traveling with speed v, and we know that it would have to travel through one complete wavelength in one period. So we could rewrite the speed of the wave as lambda, which is the wavelength in meters, divided by the period in seconds. And that kind of makes sense because this is a meter, this is a second, we get a meter per second, which is a speed. Okay, so let's substitute this expression back in for v up here, and let's see what we get. Okay, and I should have actually written a little parentheses there. Okay, so let's put that v equals lambda over t. Okay, so we have that equation now, and so now let's cancel some terms out and simplify this expression. Okay, so now this is looking something like what appears under your PRC. So we have the amplitude times the sine of this, as you remember, is the angular wave number. And this quantity, omega, is called the angular frequency. So if we define the angular frequency to be 2 pi divided by the period, that will have units of radians per second. Okay, and now we can rewrite this equation as the wave equation is a function of time and position. It's the amplitude times the sine of kx minus omega t. So again, we said that we are assuming that the wave travels in a positive x direction, And if it were traveling in a negative x direction, then we would need that to be a plus sign. Okay? And then the last thing we need to add is the phase constant. Okay, so this phi here, this is the phase constant, and that has units of radians. And that just tells us the initial conditions that arises from the initial conditions that were given in a problem. So nothing about the wave is changing in terms of how it behaves, i.e. the speed at which it travels, the angular wave number, the angular frequency, but this is like seeing it at some different time for the first time. That's all that means, and it arises from initial conditions. Okay, and the last thing we want to do is to rewrite some aspects of the wave equation. Okay, so sorry for the snafu there, but it's all good. Okay, so let's remember our variables here. So k was the angular wave number, omega was the angular frequency, so that equaled 2 pi divided by the period, and also 2 pi times the frequency in hertz, or oscillations per second. And we can also rewrite the speed of the wave as the speed is the angular frequency divided by the angular wave number, or the wavelength times the frequency. And both of these will give you units of meters per second, both of these. So that's the wave equation. And if we look at that one more time, so let's write that out again. Okay, again, y sub m, that's the amplitude or the maximum value of the displacement in the y direction. K, angular wave number. Omega, angular frequency. Phi is the phase constant. And this entire argument of the sine function here, this is called the phase of the wave. So that's part of the learning objectives. I thought I'd highlight it really quickly. Okay, so that's the wave equation, and you'll see that time and time again. So make sure that you can both kind of decode and encode a wave equation. So if you're given some of these variables or characteristics of the wave, make sure you can construct this. And then also if you're given a wave equation, make sure that you can deconstruct it and that you're comfortable enough with these equations on your reference card to say something about the frequency or the speed of the wave or the angular frequency or something like that. Okay, so the last thing for this lesson is we need to derive an expression for the speed of a wave traveling in a stretched string with some tension T. Okay, so let's first draw what we think the string would look like as some wave is traveling through it. And so that might look something like this. Okay, that's our string with some wave traveling through it. Now, let's take a look at what's happening in this very small piece of the wave right about there. So we're going to zoom in on that, and let's draw another diagram for that. Okay, so here's our piece of string or rope. Okay, and we're going to look at, this is the horizontal line that's also parallel to the direction of travel. And we can see that we have these two angles, which we'll call theta, and the string has some tension in it, and that we'll call tension T. And we know the same tension exists throughout the string, so that those are our two tensions. And if we look at this point in the middle, O, okay, so this point O is the center of the circle that this arc of string would form. So if we drew a complete circle, it would look something like this, right? Okay, and this is our radius of that circle, which we'll call r. Okay, and the wave again is traveling with some speed v. So if we look at just what's happening to this element of string as this wave is passing through, it kind of rises up and then falls, right? So we can model it as uniform circular motion of this very small piece of string with respect to the center of circular motion at O. And we also have the length of the string, as we'll call it delta S. Okay, great. So I think that's the whole picture of what's going on. And now we need to actually apply Newton's second law to determine the force that's providing the centripetal force to give that uniform circular motion for this piece of string. So let's do that now. So this is our free body diagram. Okay, so Newton's second law, remember the first thing we write is the sum of external forces equals the mass of the object times the acceleration of the object. Okay. And then if we have a coordinate axis where the radial direction is in towards the center of the circle, let's sum the forces in the radial direction. Okay, so there's two forces in the radial direction. One of those is this radial component of the tension, and this is the other one. So we have two components of the tension in that radial direction. And so this becomes 2 times the tension times the sine of theta equals mass times radial acceleration. Now if this angle theta is very small, then we can apply the small angle approximation. So the small angle approximation tells us that for very small angles, and if theta is in radians, the sine of theta is just about equal to theta. So we rewrite this equation. As 2t times the angle theta equals mv squared over r, and this v squared over r is the radial acceleration. Okay, so the next thing we're going to do is apply this relationship. So the mass of the string, or this element of the string, is equal to mu times delta S. And this mu is the mass per unit length. Of the string. So this is kilograms per meter. Okay, so that's the mass of that small element times v squared over r. Okay, and the next thing we're going to do is a little bit of a geometry trick. So we have mu, the mass per unit length, and now we have this length of the string, delta S, is just an arc of this entire circle, and that arc subtends an angle of 2 times theta here. So we're going to rewrite this arc length as two theta times r, where r is the radius of this circular motion. Okay, now it's just kind of simple math. So these 2's cancel. This theta cancels. And the radius of the circle is the same as the radius of the circular motion, so those r's cancel. And so we're left with this expression. So this tells us that the tension in the string is related to the mass per unit length of the string and the square of the speed, right? So if we do a quick unit analysis of this equation, we know mu is kilograms per meter, and v squared would give us a meter squared per second squared. Those 2 meters cancel out, so that would give us a kilogram times a meter per second squared, and that is a Newton. Okay, good. So that makes sense, right? So tension should be in newtons. Okay, so this is our expression, and again, we want to derive an expression for the speed of the wave. So all we have to do is rearrange this equation. So the speed of the wave, v, through a stretched spring with tension T, is equal to the square root of the tension divided by the mass per unit length, or what you might call the linear density of the string. And this equation is on your physics reference card, and this is one we'll have to use throughout the next board problems, and perhaps the WPR, perhaps the T, but I want to show you kind of where we get it from, and it's deriving it for this small element of string that's undergoing uniform circular motion towards this center of circular motion. So I hope this video was helpful. I know it's a little long and probably a little dry. Hopefully you didn't fall asleep. But it's something new and something I might try to do in these next few lessons. So let me know what you thought, and I will see you all in class.